All right, carrying on with section 8.1, we're studying the graphs of sine and cosine functions, and in particular, we're now going to talk about doing transformations of those graphs in order to describe waves. And you can have a wave of any amplitude, any period, with any midline or phase shift. So the question is, how can we achieve different values for these parameters by doing transformations of a sine or cosine function? So we're gonna do like all the transformations. We're gonna look at functions described like you see here, and use this as sort of like a standard format for a transformed sine or cosine function. A times sine or cosine of bx minus c and then plus d. This isn't always how you see it. There's some textbooks which set this up a little bit different, but if you encounter it in a different form or with different letters, you can always just sort of rearrange or rename things to put it back into this format and determine what the values of A, B, C, and D are. And then these right here are some formulas that you can use to calculate the values of the parameters, amplitude, period, phase shift, and the location of the midline. I'm showing you this document. This here is a little document that I've put up on D2L for you. It has the formulas, it has the little example, and then it has a couple of quick little exercises that I will walk you through later. But I'd like you to try these on your own first. So before we do those, let's go explain why these formulas are what they are. So let's go back over to Desmos and graph y equals sine of x. We're going to do this for sine, but you can, just as easily do this for cosine as well. Whoops, I just realized that I still don't have, I forgot to put these back in again. There we go. That looks pretty good. Okay, so there is our regular sine function, and it has an amplitude of 1 unit. You can see it's centered on the x-axis here, midline on the x-axis. Amplitude is 1, and normally the period of a sine function is 2 pi. You can see it goes from here, whoops, it goes from here to here. That's the period, it's 2 pi units. And its phase shift is 0. So if we come in here and start changing things, let's add some parameters. Let's put an A there. If we put an A in front of it, then A is going to scale that graph vertically by a factor of A, right? Think about it in terms of transformations. When you multiply outside the function by a number, you scale vertically by that factor. So here, if I scale this graph up by 2.5, now we have a function, a wave function, whose amplitude is 2.5. All right, so the amplitude is exactly equal to A. That is, unless you make A negative, in which case it just does a reflection over the x-axis, but the amplitude is still the absolute value of A. Okay, so I hope that idea of scaling it vertically makes some sense and explains why the amplitude will be exactly equal to the absolute value of A. So the next one is period. All right, let's think about, go back to our graph. Let's think about, instead of scaling vertically, scaling horizontally. What if I stick a value b inside here? B. Let's get rid of our a. Okay, if b is 1, we have that period of 2 pi. But if I increase b by some amount, you can see the graph shrinks down. Remember how horizontal scaling works. If you multiply by 2, you scale by 1/2, right? So what we're seeing here is the graph shrinking down horizontally because we're scaling by the reciprocal of b. So what is the new, let's say we make b equal to 2, right? What is the new period going to be? Well, the original period was 2 pi, and we're scaling by the reciprocal of the number you multiply by. So we should take 2 pi divided by b, right? In other words, multiplying by 1 over b. So we should take 2 pi divided by b and get the new period. And as you can see, 2 pi divided by 2 is pi. So that's our new period there. So let's go back to the formula. I hope that explains why the period is always going to be 2 pi, the original period of a regular sine function that's not transformed, divided by b. Now I put here the absolute value of b because, again, technically your b can be negative. If b is negative, then you're scaling and also reflecting over the y-axis, but that reflection does not change what the period is. It just changes which direction you're going. So there we go. We have small scaling, large scaling. We can scale up, scale down, whatever. Okay, the next formula is for the, let's skip the phase shift and do the midline. The midline is an easy formula. The midline is the plus d on the end. And that addition of a parameter outside the function does a vertical shift. So if I put a plus d on the end, if I add 2, it shifts up by 2, right? If I add exactly 2, it shifts up by 2 and puts the midline at y equals 2. All right, so that's pretty straightforward. That's just vertically shifting the thing up and down. Which brings us to the last one that I skipped here, phase shift, which is kind of the most complicated one of the four. If you have bx minus c inside here, let's put that in there. Put a b and put a bx and a minus c. We'll get sliders for both of these. The original sine function has b equal to 1 and c equal to 0. Let's see if I can have that 0 there. It's close, whatever. So b equals 1 and c equals 0 gives us the regular sine function. But if you increase c, you can see that that gives us some shift. If I make c positive, you're subtracting a positive number, which is shifting to the right. If I make c negative, it's shifting to the left. So shift right and shift left. So I hope you can see that. C is causing a horizontal shift. Now the reason that B is involved is because if you shift and also scale, then that affects the amount by which it's been shifted. So now the shift is different from what it used to be. Let's see. If B was 0, the shift might be. Oh, sorry. If B is 1, rather. Let's see. Let's have the shift be like about pi over 2 right here. If this was a sine function, it'd be shifted from 0 over to 1.7. But if I change b, if I scale this thing horizontally and like scale it down, that changed where my shift is. You see? So what you have to do, I'll pull up something here to show you. What you have to do is take your bx minus c and actually factor out b. Hang on a second. What's going on here? There we go. Okay. If you take your sine of bx minus c, what you have to do is actually factor out the b. And then when you factor something out, you divide by it. So you have to do c over b like that. And if you do that, then you can tell not what's being subtracted from bx, but rather what's being subtracted directly from x, like this, with the b on the outside factored out. This tells you what your horizontal shift is. So that's why the phase shift is not just c, it's c divided by b. So let's go back now to our thing. We've got c over b. Now we've got these four pieces of information here. We can look at an example. Let's see, this one right here has some piece of information for A, B, C, and D. This has all four different transformations in it. We've got the 0.5 for A, which shows an amplitude of 0.5. So here we're seeing the distance. Let's see, the distance from the midline to the peak here is half a unit. The +1 way over on the end has the shift up, which gives us a midline of y equals 1 through there. And then we've got the 2x, so b equals 2. That means we should take 2 pi divided by 2 to give us the period, which would be pi. And you can see that measured right here from point to point. Point to corresponding point is pi units. And then lastly, the phase shift comes from this minus 2 pi over 3, but then divided by the b value, divided by the 2. So negative 2 pi over 3 divided by 2 is negative pi over 3. And actually, we're subtracting pi over 3, which is a shift to the right by pi over 3 units. So there's all the different 4 different formulas at play telling us information about this wave. So the next thing I want you to do is go ahead and try out these 2 exercises. In the first one, you're taking this function as written here, calculating the amplitude, period, phase shift, and midline using formulas, and then using that information to graph it. And then in the second exercise, you're looking at a graph, measuring straight from the graph these 4 values, and then using that information to reverse engineer what the equation should be. So these are 2 types of problems you'll see in your homework. I want you to try them now, and then I will go over the solutions in the next video.